This video covers the 5 phases of testing automotive Ethernet components during the development and product lifecycle. Let's start by looking at the architecture of an in-vehicle network, so we all understand what we're talking about when we talk about switch testing and different ECUs containing switches. This is a simplified diagram of a car network based on an actual example from one of our customers. As you can see, we are working with a complete Ethernet backbone based on a 10 gigabit interface and 10 gigabits bandwidth. In green, you can see all 3 domain controller units are connected in this Ethernet backbone. We have additional redundancy for a gigabit link between 2 domain controllers even though we already have redundancy in the Ethernet backbone ring. We have different gateways in this architecture and multiple ECUs. Every device which is marked with a star contains an Ethernet switch, so these are usually the components that will be tested with the Teledyne LaCroix Xena solution. Also, an ECU with an Ethernet interface can be tested, so we can do a loopback test, for example against the ECU, or even some bit error rate testing or PRBS, and to test the PHY and functionality of a single Ethernet port. Okay, so here is an overview of the 5 challenges or phases of testing that we're going to examine in this video. The first involves choosing a switch or a switch vendor, and that process obviously starts by defining the different criteria the switch has to meet. A lot of business factors will also need to be considered, but on the technical side you'll usually do a benchmark test, like RFC 2544 or the RFC 2889, to quickly validate the performance and functionality of the switch, and then compare the results against another option. In the next step, you've purchased a switch, or a switch component, and you want to integrate this component into your product. You will do what we call a spec validation, with your own test specs. With tests based on public test specs which you can access as an Open Alliance member from technical committees like OpenTC8 or OpenTC11. You can also use the RFCs, which we mentioned in the vendor selection phase, to benchmark the integration into your device, and then the functional test based on the dependencies between the switch and the other functions within the ECU. The next step is regression testing, which is mainly an engineering quality assurance based on a fixed test plan which you have designed during the device integration. Regression testing is usually fully automated, and with this fixed and automated, you have a repeatable and comparable test result so you can go through your design and development step by step, and you can always validate on the same level. The fourth phase in the system integration is the hardware in the loop, HIL, testing. HIL is a method of emulating real-world conditions by testing and validating complex software systems on specially equipped test setups that receive data inputs from physical devices such as radars and cameras. This is done when you've added a lot more functionality and need to test the interoperability, the robustness of the system, and the overall functional integration of the system. And finally, there is production line testing and offline testing to ensure production quality. This is usually a high-volume test, so multiple ECUs being quickly tested according to a reduced but focused test plan that is fully automated for rapid execution. So firstly, the design. What do you need in your environment? Do you just need a chipset and you're designing your own switched environment? Or do you need a switchboard to put into your ECU? Or do you need a completely independent switch device that can be used as it is in your network, or used in an ECU box as an independent switch? Every switch has specific metrics like the speed and the PHY, so it can be 100 megabit PHY, or a gigabit PHY, or a dual speed PHY. Will it be just base T, a classical Ethernet with RJ45 like we see in the image, or do you want to design it specifically for automotive Ethernet like base T1? And how many ports will you have? And do you want different speeds on the switching device, for example, 1 gigabit and 10 gigabit? Similarly, you will need to define which protocols your switch should support. Is it just classic IEEE 802 dot, with VLAN, which is usually also standard in every switch? What about overall performance and interoperability? A non-blocking architecture is a term you probably know from the Open Alliance TC8 or TC11. And basically it means you want to ensure that all ports are operating at line rate, so you can expect maximum performance without losing any packets. Is there an average delay requirement from your application? Or an average or maximum jitter requirement? Do you want to know the startup time of the switch? So how long does it take the switch to be operational when you power on? There could also be traditional test specifications like RFC 2889, which is a switch benchmarking test specification, or RFC 2544, which is a device and network benchmarking specification. Other tests that are often overlooked are robustness and security requirements. For example, VLAN separation. If you have multiple virtual LANs in your architecture like infotainment as a virtual LAN and ADAS, Advanced Driver Assistance Systems, as a virtual LAN, then you want to verify that no traffic can go from one VLAN into the other VLAN. Similarly, what happens if you have a broadcast storm? Is your switch robust against it? And how are the redundancy functionalities? Are they sufficient? So now let's look at the device or component integration test phase. For this, we need to take a deeper look into the device. If we look at a domain controller unit, we can see it has multiple function areas. There are two switches involved, a 10 gigabit switch and the Automotive Ethernet switch. There is also a CAN/CAN-FD module, a diagnostic module, a shared memory, and we have the domain application. There is probably a gateway as well, and then the core microcontroller or FPGA, which is processing the data. The important point with the integration validation is to test the Ethernet communication. Often people will say, okay, but I tested the Ethernet switch already in the initial step. Why should I test the switch again when I integrate it into my ECU or DCU? It is important because as you have dependencies within such a design, you probably have less performance or less memory if you are changing specific configuration on the domain application. So you must revalidate the communication through the Ethernet switches to verify it always works as expected or described in your specs. Also, you should do a full test of all Ethernet ports in a fully meshed environment because later, when you put this DCU into a network, it becomes part of the whole solution. And if you have specific problem on one switch, it can influence the whole network communication. So what you're doing is the functional test, the performance test, robustness test, with dependencies to the other further applications you are running in your DCU. If we look at the engineering process, this is usually done in the A sample to B sample. So that's done with partial functional hardware and software. So you will not have all test results as checked, but in the different stages you should add more and more tests here. Now let's look at a quick video of how an RFC test works. This is the RFC 2544 test suite, which is always included in your Xena test solution. You can also try this on your own if you want. Just go to Xena's website and download the software, and then you can connect directly to our live demo system in Copenhagen and do the same as what you see here. So now we are connected to a chassis and selected a specific test module, in this case, a 6-port 1 gigabit test module. We then choose 2 ports, setting up the test topology, which is fully meshed and bidirectional test direction. So we're sending and receiving at full line rate. We set up a specific frame size, in this case 512 bytes, and then we go to the Test Types Configuration tab because we have multiple tests running in an RFC test, and we can pre-select which test we want to do. In this example, we are just doing a throughput test and then a latency and jitter test. Now we are reducing the duration for this demo so that it's not running for 100 hours. You can also do a specific protocol selection. So Ethernet is standard. You can also add VLAN, or you can add IPv4 addresses or even IPv6 addresses. With this, the main configuration is done, so we can now start the test. To make things easier, you can save the test configuration and then the test suite will configure the ports and configure the streams and automatically start the test, and we can now see results popping up here on the bottom of the screen. So the latency and jitter test is being performed, and when it is finished, The Xena 2544 application will automatically generate a test report and save it as a PDF file, which looks like this. This is a very simple report, and as I mentioned, you can try it yourself using Xena's live demo system in Denmark. Now let's look at the third challenge, which is regression testing. Regression testing is done during the main development process, after the initial integration of your hardware and software. In this phase, you will often change the software and the firmware, but you're not expecting to change the hardware. Now you want to continuously monitor the performance and other metrics like delay of the switch if something changes or goes wrong when you make specific changes. Regression testing typically involves using predefined test scripts so you can repeat the same tests every time. It is a good idea to keep the tests simple, so the results are presented as pass or fail. That way you only need to look at the results that are not okay. The setup is pretty simple. As you can see, we have a Xena Ethernet tester, plus some other third-party test tools for testing CAN/LIN or other technologies on your ECU. You're doing REST simulation for functional testing of the application, and combined this gives a complete view of the functional quality or the validation of the system. Everything is probably automated through a third-party test management quality system like LabVIEW from National Instruments, or you're using your own test automation tool to automate any third-party test tools. Xena Open Automation provide full control of the Xena network test solution for this kind of integration. Usually this is done from sample C to sample D, meaning from partial to full functional hardware, software up to the production-ready sample D. We also support different development methodologies like waterfall or agile, so this approach can be used in all these types of processes. Test automation is important in regression testing, so all our test solutions have a REST server implemented in the Xena solution, so you can use every kind of REST client. You can also use Python or even a simple command line bash tool to do the automation. The following stages is known as hardware in the loop or hill testing, and this is where we go from testing components to testing whole system. This is where the single device is integrated into the physically available or partially simulated full system, like the Ethernet backbone, the ADAS domain, infotainment domain, or even the whole vehicle's electronics. The related automotive development stage can be described as sample C/D, fully functional hardware and software, or production grade. The main purpose of hill testing is to validate the system functionality. But why do we need to test the switch or even the network functionality once again? During the initial vendor selection stage, we already validated the interoperability of the switch integrated in the device under development. However, within the whole system there is a high probability that some ECUs are from third-party vendors, and there's no guarantee that these devices are fully compliant with the general switch and networking specifications. Also, the behavior of single device integrated into a network can be different compared to a standalone test of the switch functionalities. It is critical for the main hill test process to ensure a 100% working and performing communication infrastructure made up of the actual switches and the network built with those switches. If this isn't done, it will be difficult to find out if the failure was caused by an application error or a network communication error. The most efficient approach is to validate the communication layer first so you can exclude the network and any subsequent troubleshooting. The required test plans include a subset of the test cases executed in earlier stages, together with some new test scenarios. These are mainly related to 1. Core switch and network performance metrics, like end-to-end performance simulation of the Ethernet end devices. 2. Network impairments like jitter, delay, and packet loss to validate redundancy. And 3. Robustness and quality of service testing to validate the overall network functionality. The final phase is production line testing. As I said, that's mainly for Tier 1 or Tier 2 suppliers or chipset manufacturers, because I don't see Ethernet testing performed in the end of line of a car, so we will not put an Ethernet test tool to a whole car. That's more to test end-of-line the ECUs or specific end devices. As I mentioned before, end-of-line testing will be a reduced test focus on very specific metrics like a PHY speed, so you will double-check the auto negotiations separately or if all PHYs are configured to the correct fixed speed. Testing the signal quality, you're doing a quick check of the non-blocking architecture, a couple of seconds, you probably do a bit error rate test or a pseudo-random bit test. You do the VLAN configuration check and probably some more custom metrics to be checked. These tests need to be very fast, reliable, and reproducible, like the regression testing, to have a continuous quality model. Also, it is important that you can handle a high device under test quantity in a very short period. In other words, multiple devices under test or multiple ECUs being tested at the same time. The test setup is also pretty simple. So you have again a specific test system such as a Xena B chassis, which has 12 slots giving you up to 72 times 1G test ports, which can be connected to a third-party test management and automation tool or to the Xena Manager software, which you will hear. And then this test tool or system is connected to the test stand where you can put in multiple ECUs or multiple devices to be tested in parallel. And again, this is engineering cycle full production, and even the ECUs can be changed automatically by a robot, for example. These tests are designed to run for extended periods. We have seen installations running over 40 days without any reboot of the system. However, if it is fully automated, you will probably have to do some support on this every month or so. The test stand can be everything you can imagine: temperature chamber, a traditional test stand, an EMC test stand where you probably change from copper to fiber and back again to copper to have full electromagnetic compatibility. Here's a quick video of a customer's production line test system in action. You can see the test engineer is pulling out the switchboard to reset the test, so when he puts it in again, the test stand will automatically read which system it is and the serial number. You can see the LEDs come on, meaning the links are up and running. Then we're going to the test system. We can see how it reads out everything, configures the test, and starts the test. And when we go back to the system, we will also see that the LEDs will flicker for a second, indicating traffic is running. So why is switch testing so important? In the past, if we talk about Canvas, the network was just a wire, and most of the intelligence was in the end device and the interface. But today, with Ethernet switching and Ethernet networking, we have a lot of intelligence in the network, so it's critical to test the interoperability between switches. A network is only performing as fast as the slowest device. Every Ethernet switch can impact communication across the entire network, so it's very important to view the Ethernet communication as an additional layer for the application. If there is a misconfiguration or some other problem on this communication layer, you will also have problems within the applications. So if you don't validate these Ethernet communication at the beginning and revalidate them all the time throughout the engineering process, you will potentially have a lot of problems to troubleshoot in the higher layers later on. If you have an engine control unit which is not receiving specific messages or data, you won't know if there is a problem in the application or in the network. With Teledyne LaCroix Xena, our tagline has been, test, improve, repeat, which means you should test all components in the whole engineering chain so you can troubleshoot and resolve problems immediately. Then you can go and perform a repeat revalidation to prove the final functionality of your hardware and software. Finally, I want to show the Teledyne LaCroix Xena solutions for Automotive Ethernet switch testing. Firstly, there is a dedicated Automotive Ethernet test module with 6 dual-speed 100/1000 base T1 ports, which is a bus system that will probably replace CAN or LN in the lower speed side. This test module can be used in 2 different chassis. There is the Xena Compact, which is just 1 test module, so only 6 test ports. Or you can choose the high-density Xena B720 chassis, which can hold up to 12 test modules, so you can have 72 times 100 or 1000 base T1 ports. All our systems include the Xena Value Pack, means all the software included. Plus you get 3 years software updates, 3 years hardware warranty, and also free tech support and training for the lifetime of the product, which, combined with the low price per port, makes this a very cost-effective solution for testing Automotive Ethernet, as there are no extra expenses for at least the first 3 years. All right, folks, Thank you very much for listening in. To learn more about Teledyne LaCroix Xena's solutions for automotive Ethernet testing, please visit our website.